is a great pleasure to have here today Marcelle Soares-Santos. Thanks a lot for accepting our invitation. Marcelle is a full professor at the Physics Institute of the University of Zurich. Previously, she was an associate professor of physics at the University of Michigan, Landsman Career Development Chair and assistant professor of physics at Brandeis University, and associate scientist at Fermi National Accelerator Laboratory. Marcelle's research focuses on uncovering the nature of the accelerated expansion of the universe. She contributed to the construction of the Dark Energy Survey Camera, that is one of the largest telescope cameras in the world, which she has used to search for gravitational waves emitting collisions of neutron stars and black holes observed by the LIGO-Virgo-KAGRA collaboration. Her program aims at establishing gravitational waves as a completely novel method to study cosmic acceleration in the universe. It has been successful in detecting the first neutron star collision ever observed, a discovery heralded as the science breakthrough of the year in 2017. She was awarded the prestigious 2023 EPS Fellowship, 2021 Kotre Scholar Award, and 2019 Sloan Research Fellowship. Marcelle also contributes to the effort of measuring the cosmic acceleration using traditional methods, such as galaxy cluster and gravitational lensing. Marcelle's research has been featured in the PBS documentary TV series Nova Wonders and has been covered by major news outlets worldwide. Today, she will present multi-messenger cosmology with cosmic surveys and gravitational waves. Marcelle, please, you can start when you're ready.
Thank you. Thank you for the invitation to speak here today. I'm going to share here my slides and put them in slideshow mode. All right. Thank you again for having me here today. Thank you for coming to this presentation. So today what I'm going to do is to talk a little bit about more recent results from, in this field, in particular recent results that my group here at the University of Zurich has contributed to. So our goal as an experimental group focused on cosmology is to study the nature of physics at these cosmic scales, what's going on with the cosmic acceleration in the late universe, and if possible, have something to help resolve this late and early universe tension that we, I think in cosmology, have been very worried about. In this talk in particular, I am going to present, as I said, recent results, and in particular results that come from data sets of the Dark Energy Survey and the LBK. Our key science questions have to do with the physics of dark energy, the unknown component of the universe that causes the expansion of the universe to accelerate in the recent, the last 5 billion years. We don't know if dark energy is a cosmological constant or not, if it is, physics beyond general relativity, but we know that we need to improve our observational techniques, our analysis methods in order to study and try to resolve this question. Dark energy in particular is a field where I think we have been very fast evolving. It's a field where within about 30 years, we went from discovering that accelerated expansion was happening to really building up a precision measurement program worldwide, right? That involves many different experiments with different approaches, new techniques, and so on. When we talk about doing dark energy research, oftentimes we talk about measuring cosmological parameters. In particular, I'm listing here some of the most relevant ones that often come up. The equation of state of dark energy. As you know, if dark energy is the cosmological constant, this W is exactly equal to -1 and does not evolve with redshift. But otherwise, it can be something that has a slow evolution, and we parameterize it often in this form where we try to measure the 0th order term, W0, and the first order term, WA. There's also the clustering properties, because dark energy would hinder the formation of largest scale structures in the universe. So clustering would also be affected. And the parameters there are, depending on what paper you look at, sigma 8 or S8. And the other big important parameter is the rate of expansion of the universe today, H naught. And finally, but not less important, is the energy density of matter today, omega m. So these are typically the parameters that we talk about. And when we talk about measuring these cosmological parameters, we want to make sure that we get consistency, meaning that models that predict so two different models should not only correspond to the same expansion history, but also should correspond to this, they can be differentiated by how they affect the clustering. So we want, in principle, to have an ecosystem of different experiments that can allow us to measure expansion history, growth rates, and constrain these parameters with maximum possible precision. And on top of that, what we would like to do is to have observables that can go from the modern universe where dark energy is being dominant today, all the way back to the early universe, so that we build a consistent picture of the evolution of the universe across cosmic time. Well, as you probably know, that consistency is being challenged lately, right? And oftentimes we talk about tensions or anomalies. And what does this mean is, in a nutshell, that depending on whether you use galaxies, which are obviously in the late universe, or if you use the cosmic microwave background data from the early universe, you get different answers under the assumption that dark energy is lambda CDM, or that dark energy is the cosmological constant, right? The lambda CDM model. And this is illustrated here. On one side, this side here, you have sigma 8 omega m, and this is one of the typical plots that people use to show that, oh, maybe there is something that is inconsistent when we look at measurements based on the CMB and measurements based on late time observables. The other one, which is most famous, is the H naught tension. And this is showing measurements of H naught. This plot is a few years old, but it shows measurements of H naught as a function of year of publication, separated in two types of probes. Here, standard candle-based probes, supernova, and in red here, the cosmic microwave background. And the key take-home message here is that the discrepancy between these two, early universe and late universe observations, is growing, and the more precise the data that we get, the worse this tension seems to be. Now, the multi-messenger aspect came to the picture relatively recently. As you know, it's been about 10 years that we have developed the capability of observing gravitational waves. And the promise there is that, well, gravitational waves can be used as standard sirens for distance measurements, and it could actually be an independent arbiter between these two different probes. As you can see here, this is the result obtained with one standard siren, GW170817. And well, this here, as I said, is a plot from some years ago, was projections. We expected that by now we would have something like 15 of those, and we'll be measuring H naught with this precision here with gravitational waves. As you know, the story gets a little bit more complicated and more interesting than that, but I think that this is a good summary plot to illustrate the situation. Now, this is a rapid evolving field. Within, the last few years, I would say last 2 years or so, new results have shown that the tension on the clustering side of the picture has mostly gone away. It is alleviated in the most recent analysis. However, the tension on the Hubble constant, it's alive and well. It is still there, and it doesn't seem to be going away anytime soon. So what does this mean? It means that either we have some systematic uncertainty on either CMB or late universe observables that we would have to take into account, or there is really some new physics, and that new physics could mean that dark energy is not the cosmological constant, or could be something that is wrong about our picture and understanding of the physics of the early universe and so on. In any case, it is exciting because it means there is a lot of physics for us to do in there. So I mentioned some of the parameters that are relevant, and I mentioned the problem of the tension, early universe, late universe. Now I would like to present a list. It's not complete by far, but a list of the types of probes that we use when we want to study this problem observationally. So type 1a supernova, I already mentioned. The standard sirens, I have already mentioned. Galaxy clustering. There's also gravitational lensing, and obviously the cosmic microwave background. The idea here is that some of these probes are more sensitive to the expansion history, others to growth of structure, some are early universe, some are late universe, and the idea is that, the full combination of these probes should be powerful in constraining the cosmological model and helping us maintain systematic uncertainties under control. So here is an example that will be relevant for us here today. And this is the so-called 3x2 point framework. So in this framework, you combine three 2-point correlation functions. One of them is the correlation function of galaxy positions. And the idea here is really that clustering that you're measuring via that. The other one is the correlation function of galaxy shapes. The idea there is that because of general relativity, we know that the path of light of a source that is behind a massive structure will be distorted by the presence of that massive object. And statistically, then, if you have a distribution of galaxies, you will have that the shapes of the galaxies will be distorted. And the statistics of these shapes can be used also to constrain cosmology. The idea here is similar to the 2-point correlation function of positions, but now instead of points in the sky, you have vectors that indicate the distortion, the shear, due to gravitational lensing. And finally, the third 2-point function that we use in this analysis framework is the cross correlation between the position of the galaxies and their shapes. Okay, so this so-called 3 times 2-point framework is very powerful because it combines the three observables into one analysis and to get us cosmological constraints that are very strong and also that are very robust against systematic uncertainties. As you know, these analyses are all deep in the systematics limited regime. So systematics control is really important. So this cartoon here is trying to illustrate how these three analyses work. The illustration here, as you can see, this is representing the telescope that we used for the dark energy survey, and that I'm going to talk about results from that soon. Now, let me go in a little bit deeper into the standard sirens as a second topic, because it will also be relevant for our analysis later, analysis results, I mean. And here is, I think there are three different cases that I would like to discuss. One of them is the most direct case where you have a gravitational wave signal represented here. So this is GW170817. This is what the signal looked like in the LIGO-Livingston gravitational wave detector. So here is a time frequency plot, by the way. So when the chirp occurs, the shape of this signal here can be used to determine the distance to the source, the luminosity distance. And if you can obtain the redshift information by some means, you can use these objects to build a Hubble diagram, distance versus redshift relation, analogous to what we do with type 1a supernova. Well, this idea is an old idea, but it was possible to realize this only recently when the technology came for detecting these gravitational wave events. Here is the GW signal of the gravitational wave signal, I mean, for GW170817. And this is the image of its electromagnetic counterpart that was found approximately 12 hours after the merger. And this was important because by identifying where the object is in the sky, you can take the redshift of this object or of its host galaxy, and you can use, these objects as a bright siren for this type of cosmology analysis. That's great. But what if you cannot find the electromagnetic counterpart for some reason? That reason could be, for example, that the merger could be a binary black hole merger that emits no light, or it could be poorly localized in the sky and you're unable to find a counterpart, or it could be too faint, or a number of reasons, right? Well, in that scenario, it is still possible to use these objects for cosmology using an approach that has been called dark sirens. The idea here is that you take the distribution of galaxies in the region of interest. So here's another event. This is a binary black hole merger, we think, GW170814. And this here is a 90% probability area, and the inner contour is 50%. The color map underneath is the galaxy distribution from the DES data. And the idea is that now this galaxy distribution can be used in a statistical way to provide redshift information for the analysis. Now, you can imagine that because you don't know which galaxy is actually the host, this analysis will be poorly constraining on an event-by-event basis. The good news, on the other hand, is that these dark sirens are much more numerous than the bright sirens. Presently, we have about almost 300 to 1 ratio between these two. So the idea is that once the statistics gets better, this method could surpass the bright sirens method in terms of sensitivity. And here's result from an old a paper from a few years old already. That was one of the first papers doing this type of analysis. And here what you can see is in light blue is the result from corresponding to this event, GW's 190814. The gray contour is what you obtain with the bright siren. As you can see that these are, mismatched in the sense that with the bright siren, you get much more constraining power per event, as expected. And the dark blue here is a combination of two events. This one plus another one that happened about 2 years later. And the overall red curve here shows the combination. So you already see where we're going with this, right? Ideally, what you would do is that you would have for as many objects as possible the bright siren approach, but also you would combine them with the dark sirens that are very numerous and do a joint analysis combining both of them. But there's more, right? There is a third way of doing this, which is the spectral sirens. And this method is newer, and the concept here is the following. The idea is that if you have no galaxy information at all, you can still get some cosmology information if you have a sample of gravitational wave events, and you have features in their mass distribution. The idea here is that the key problem that you cannot get redshift information directly from gravitational waves is the degeneracy between the object mass and its redshift. But if you know what is the distribution of masses intrinsically, then you can use that mass distribution to help break this degeneracy and get redshift information out of the gravitational wave data itself. These methods, these two papers that I'm mentioning here, have been some of the early implementations of this methodology in real data. And you can see here that, again, you can get, so this is constraints using a sample of, so it's not individual events anymore, but a sample of dozens, many dozens of gravitational wave events, and you get some reasonable constraining power here. GW170817 is the black line here for comparison. So great. Ideally now, what we would do is combine all these three methods in a super analysis to get the best out of all of the standard sirens together, right? All right. So as already mentioned early on in the introduction, this talk is going to focus specifically on cosmology results that come from the Dark Energy Survey and from the LVK data sets. Our group is also involved in LSST, the next generation large-scale ground-based survey, imaging survey. And we are also members of the Einstein Telescope collaboration, which is planned, for the future. But today, what we are going to do is specifically talk about the results from the state-of-the-art data sets. The DES, for those who maybe are not familiar with, I think in this audience, everybody knows it very well. I have heard about it. The DES is a survey that used a camera called the Dark Energy Camera. This camera is shown here. So here what you see is a much younger version of myself in front of the focal plane of the camera. That was one of the largest cameras, built at the time, with 570 megapixels. And this camera was installed on the prime focus of the Blanco telescope in Chile. So the Blanco telescope was a telescope that was already there from the 1960s and 70s. And the DES collaboration built the camera and installed this camera as part of a large upgrade project of the entire telescope and pursued this survey. The survey started in 2012 and was completed. The observations of the survey were completed in 2019. And what you're seeing here in this sky map, this irregular shape here that I hope you can see my mouse around, is the footprint in the sky of the Dark Energy Survey. This footprint adds up to 5,000 square degrees, and it was observed in the optical and near IR bands, GR, Z, and Y. These little patches in white here are areas, small areas, where we did deep observations for supernova, for the supernova component of the DES survey. So DES did not only the 3x2 point type of analysis and clustering and weak lensing, but it also had a supernova component as well. Other things that you see in this map that help put it into context are other surveys out there, including what you see here in green is the footprint or the northern limit of the footprint that the LSST will cover, which will be, as you see, the LSST will cover all this region, will be much larger once it's completed, right? But at the moment, we are going to focus on the DES data set here. So I said that we are going to have DES and LVK. So let me talk a little bit about the LVK. So LVK, as you all know, it stands for LIGO-Virgo-KAGRA. And the idea here is that these gravitational wave observatories, they operate in a coordinated way because when the same signal is seen by more than one antenna, that is helpful in determining its physical properties and also in localizing it in the sky. So the images you're seeing here are of the LIGO, the two LIGO detectors and the Virgo detector, and here also KAGRA, which is on the ground. As you know, these observatories have been operating over the last 10 years, and not continuously, of course, because there are always, breaks for upgrades and so on, commissioning breaks and etc. But let's say over the last 10 years, we have this technology available for gravitational wave observations. And particularly, this plot here on the right is showing a collection of the mergers that were detected by the LIGO-Virgo-KAGRA network. And so the way you read this plot, you probably have seen this many times already, is that each pair of dots here are two components of the binary that merged and formed the bigger object there. All of these are mergers detected by this network. And these ones here that are unpaired are other compact objects, black holes and neutron stars, that have been observed without gravitational waves, just with traditional telescopes. What you can see here is that, well, we see a much larger population of these than before. And also in terms of masses, we also have now a better understanding that these objects are more numerous and more massive than we had anticipated with previous astrophysical models and previous observations, which is very exciting. So in total, the latest data release from the LIGO, so the latest data release from the LIGO-KAGRA collaboration includes events detected up to about January 2024. And of course, as you know, there's been more observations since then, and there are more observations planned in the future as well. So contrary to DES, which is done with its observations, here we are talking about something that is still ongoing and very much so. All right, so now that we set up the stage, we talked about the elements that go into the analysis. We talked about the facilities that provide these data sets that come into the analysis. So now let's have a look at some of the results. The first result that I want to show is the DES-Y6 3x2 point result. So Y6 here means year 6, meaning the full data set from the DES observations. And this result came out earlier this year, so it's very fresh. I'm very excited about this, that after so many years of work in this collaboration, we are at a point where we have results to show like this, the final results. So in this case, what we did was constraints on lambda CDM. In particular, I'm showing here a subset of the plot. So this is the familiar S8 omega M plane. And the pink results are the DES 3 times 2 point result. In orange is when we combine as well with supernova and BAO. As I told you, DES also did supernova observations and so the DES altogether, everything together analysis leads to this orange region. And the CMB result is here. So this is another place where you can see that the tension in this space, at least, the tension doesn't seem to be there. On this other side, what we are seeing is again on the x-axis omega m, but on the y-axis, what we have is the equation of state of dark energy. Remember that -1 would be the cosmological constant lambda. And as you can see, our results are very much consistent. Orange again is the full combination of all of the DES probes. And our combination is very much consistent with a cosmological constant here. So I would say also that in this talk, I decided to try to highlight some of the names of the people from our group who are, leading efforts and contributions to some of these papers, because as you know, in these very large collaboration papers, we have often the big alphabetical order thing. So I think it's good to give a chance to let some of the people shine here and show their work. So this is what we have on the main DES-Y6 result. Now let's switch to gravitational waves. So the latest result there from gravitational waves, the key person from our group working on this has been Danny, who has been working really hard on this analysis that includes the latest data set from LVK that we call the GWTC 4, so transient catalog number 4, version 4.0. And this analysis includes all 3 standard siren subchannels, meaning the bright siren, GW170817, the galaxy catalog approach, and also the spectral siren approach without galaxy catalog. Here, for the galaxy catalog, I should say that instead of the DS, the catalog that was used was an all-sky catalog called the Glade Plus catalog. There are details here in this paper. You can go there and have a look. And what you're seeing here is the posterior distribution of H naught. The vertical lines are corresponding to the CMB and supernova, which we know are in disagreement with each other. And as you can see, this result is not really yet at the level of being precise enough to have something to say on this late universe, early universe tension. But you can see already that it's making progress, a lot of progress relative to the early days where this curve looked really, really much more broad. The key thing to notice here is that, so the yellow one is GW170817, the one and only bright siren so far. Orange here is the spectral sirens, where no galaxy catalog is used, only gravitational wave data is used. Blue is when you include galaxies, right? So you add the galaxy information, you get different constraints here, maybe a little bit better. And the black curve here is the combination of everything together. In this analysis, there were 142 gravitational wave events used in total out of the 218 that have been published with this catalog, okay? So I talked about the DES result. I talked about the gravitational wave result. So now let's start put the 2 things together. So in this paper, which is came out earlier this month, we started to say, okay, now let's see what happens when we do this gravitational wave analysis using the same LVK latest and greatest data set, plus the latest and greatest galaxy catalog from DES. Now recall that DES is not an all-sky catalog. It covers only 1/8 of the sky. But our rationale is that this catalog is much deeper than with the Glade Plus catalog. And you can see that in this bottom panel here. So here's again the footprint of DES in the sky. Sorry, this is mirrored with respect to the previous version I showed, but you can mirror it in your mind. And the regions here are contours for the events that overlap with this region. And these same events that overlap there are shown here in the bottom panel, where you can see them just, the ranking here is by volume. The most well localized by volume are expected to carry more constraining power, obviously. And on the bottom here, you see is the expected moving volume distribution for a fiducial cosmology and the distribution of the DSY6 galaxies. The NDZ is on the right y-axis here. So here there are something like 15 or so events that are included. Some of them contributing a lot more than others because some of them are not so well localized. The GW 170814 that I showed the picture in the previous slide is this orange one here. It's one of the most constraining up to now. So what is the answer? The answer here, as I have already probably anticipated, is that we do enhance the cosmology constraining power with this catalog with respect to the previous analysis shown here. And why? Because although the area is smaller, the depth of the DES catalog, which in this analysis, we actually cut it somewhere here to avoid these issues with these peaks here that we think are not physically there, that we think they are systematics. But you can see that if we use a much shallower catalog, you're going to let's say, the contribution from the events here will be limited, right? So there's a trade-off between area and depth. And here, the results, so these are again posteriors of H naught, similar to what I showed before. And what you have here that I think is relevant for comparison is the green dashed line is the result from the previous paper that I showed before. And if we compare that with the red line, which is from this paper, you can see that there is an improvement in constraining power. So what's the bottom line here is that depth is an important component. Going deeper is more expensive. These galaxy catalogs are more difficult to build, and you also are going to be susceptible to more systematic uncertainties on your redshifts and so on. It's hard. I really encourage you to look at Isaac's paper because there's a big discussion about these potential sources of systematic uncertainties. But I think it is worthwhile because otherwise we are leaving, say, constraining power unused, in these data sets. So that is more or less the lesson learned here. And we hope that for the next data set from LVK, we'll be able to use a deeper galaxy catalog such as this one. All right. So what is next? The next result that I want to show is a combination of the standard sirens type of analysis with the 3x2 point analysis. So it's I think that this is really taking the multi-messenger concept to another level here. As I said before, the idea is that these type of combinations, they have the opportunity to be more than just the sum of its parts, in the sense that you get better constraining power, maybe better handle on systematic uncertainties, and so on. So this, I think, to my knowledge, I think was the first attempt to do this, combining 3x2 point and standard sirens in the same analysis. For this one, I should note that we worked on this analysis before the DES Y6 3x2 point result was available. So we used a previous version that was the Y3, okay? And obviously stay tuned, because we are going to put an update out now that there is a Y6 data. This part of the analysis on the gravitational wave front is is really the part that the same as you saw before. Okay. So what do we have here? I think I will start with this plot that shows again posterior distribution, and here again H naught. And what you're seeing in the solid curve in blue is what we get for 3x2 point alone. So normally we don't really talk about the 3x2 point as an analysis that is particularly sensitive to H naught. We really say that this observable is more sensitive and more suited for the measurements of sigma 8 or omega m, that's where this bulk of the sensitivity lies, but there is some sensitivity to H naught here. And on the other side, the dashed orange line is what is obtained from the standard sirens. Now here, note that instead of using all of the 3 channels of sirens here, we used only the spectral sirens that don't use galaxy catalog. Why? Because you're using a galaxy catalog here, and here we would be using another galaxy catalog, and there would be some overlap between them, and there would be systematic uncertainties and covariances and so on. So to avoid all of that and make a cleaner and simpler analysis, we used only the component of the GW side that is galaxy free, so to say, right? That doesn't use galaxies. So the combination of the blue solid and the orange dashed is the black dashed curve. Obviously, the constraining power here is, no, it's not better because we combine the two, right? And we get this result. Now, finally, if we add the bright siren, okay, so I should say that here for the black line, we added the bright siren information, GW170817, and in particular, we also included information about the jet, that basically about the EM side, that allow us to even improve more the constraining power there. So that is what we obtain. That's the black solid line. And the overall precision of this measurement is 6.4%. So I think this is a very exciting and promising result now. And in the future, I think that this type of approach can really help us reach the level of, precision cosmology with gravitational waves that it may help us get there sooner than we would otherwise expect. Now, something that was surprising to me when we did this analysis is shown here on the left side. So this is H naught omega m. And the color coding is the same. Blue is the 3x2 point alone. Orange is standard sirens alone, and black is the combination. And what you can see is that this analysis also improves the constraint on omega m. Specifically, this improvement is of 22%, which is not negligible, right? So as it turns out, this combination is something that is powerful not only for this specific H0 parameter, but beyond H0, even though the standard siren analysis per se is not sensitive to H0 at all, as you can see here. I mean to omega m at all, as you can see here, sorry. But the way this degeneracy here in this parameter space from these multiple probes turns out to be, the combination actually helps. So I thought that this is also very exciting, and I hope that the subset of the cosmology community that is working on, weak lensing surveys and so on, will be excited as well about this and will want to use these combinations in their papers as well in the future. This type of combination, of course, with more sirens and so on. And in this case, for this paper, we really put together expertise from both sides here of the EM and GW side to really push this out. All right, I am approaching here the end. So what I'm going to do in this final act is give you a little bit of my perspective on where I think this outlook looks like for the future. On one side, you all are aware, I think, that the new era of imaging surveys has begun with the LSST. I'm very proud that our group has been very involved in the LSST camera project, helping with the commissioning and being there during first light and so on. And this for me represents, I think, a bright future for us because not only we are going to have, more um, more area, more depth for the standard siren approach, but we also will have a spectacular 3x2 point analysis that I think that based on what we showed here, it really looks like it will be very powerful. So I'm very excited about this. On the other side, something that is also expected very soon is more LVK data. As I mentioned before, the GWTC 4.0 contains data only from the first part of the latest observing run, 04. So there are two more batches of data that are already in the can and that should be released in the near future. And of course, we expect that the constraining power will only increase there because the statistics will go up. In addition, as you probably have heard, the LVK has recently announced the next observing run. And that will happen in the not so far future. So what we expect here is that we are going to get, more data for all this type of analysis from both sides, from the EM side and from the gravitational wave side, which will be really exciting, So in summary, I believe that there is a bright future for cosmology with multi-messenger observables using not only, I think that oftentimes when we think about multi-messenger cosmology, I think oftentimes people think about the standard sirens, multi-messenger with finding the EM counterparts or maybe extending to multi-messenger with the galaxies. But I think I am thinking of, a superset of multi-messenger cosmology analysis here that include what we traditionally think of EM only, galaxies and lensing and so on, with standard sirens together, taking advantage of their complementarity to really get to make progress in cosmology faster than we would otherwise. So I think that especially with the upcoming new data releases from LSST, from LVK in the next few years, these things take time and take a lot of preparation, of course, to happen. But this is happening now, and I think that this will be very exciting for our community. So I think I'll stop here. Thank you so much again for listening and for having me here, and I will take questions.
Thank you so much. Thank you. Very, very nice talk. Do you have any questions? Okay, I think I can start then. So at the beginning, you show us the plot of the Hubble constant, where there was like the distance ladder, and then the CMB, and there were forecasts for the for the gravitational waves that you said. Unfortunately, we didn't reach that precision now. So
Mhm.
first of all, I would like to know, okay, what was the problem? So it's just a problem of statistics, and then if there are new forecasts for the future telling us, okay, what precision can we reach on each knot in
Mhm.
gravitational waves?
Yeah, so that forecast was assuming that we would find 15 gravitational wave events like GW17 or 817 with EM counterparts identified and so on, right? And that has not happened in part because maybe uh, nature is being a little bit mean to us, because the rates of binary neutron star mergers are maybe not as high as we had hoped, right? But so that maybe is one problem. But on the other hand, I also think that it also means that I think that the attention has shifted to these other methods, dark sirens and so on. And there, on the other hand, the rates have been higher than, I mean, consistent within the large uncertainties that we had early on, but more on the higher end of that. And I think that these methods are proving that they are evolving and quickly. So I think that that is yeah, to answer the first part of your question, I think that is the reason. On the other hand, something I did not mention is that the community is working towards the next generation of gravitational wave detectors, something that would be the equivalent, what LSST is to DES, right? And I think that in that scenario, the forecasts are spectacular for the number of events that we are going to get and the precision we will hope to achieve. Now, on the other hand, I also hope that we get to percent level precision with gravitational waves maybe before the Einstein telescope is built, because that will take some time, right? But overall, I think that we will eventually have many more events to do an analysis that is purely EM based with high precision. It may take a while, but we'll get there.
Okay, thank you so much. And Umut?
Uh, yes, thank you, Marcella, for a great talk. Maybe I might have missed the beginning, but and Eleanor already asked some part of my question relating to bright sirens. So, is there any like specific paper that is calculating the ratio of dark sirens to bright sirens? What is expected to, like for us to discover in the next 2 years or 3 years? Because from this,
Mm-hmm.
what I understand, we only have one, maybe two, but I think one is usable. If we have two more in the next 2, 3 years, we can constrain like H naught
Mm-hmm.
much better. But what is the likelihood of that happening?
Yeah, so there there are some papers. So the thing that comes to mind actually is there is a public web page that is maintained by the LVK with prospects for detection, etc., and some estimates of probability of detecting BNSs and so on. I haven't looked into that page in a while. The last time I looked was somewhere halfway through '04, you know. And again, the uncertainties on the rates are very high still because so small number statistics. So and I think it's hard to predict, but overall the expectation is not to get tens of those in the next run. I think it would be surprising if we get tens, but one or two we are all hoping for, right? With some luck.
Okay, so this means we were lucky to detect that first one because I mean it was on for a small amount of time and we discovered bright siren.
Yes,
we
I think that
were
the fact that we have not observed another bright siren, it was not for lack of trying, right? So there are programs out there. We one of the things we do actually in my group is to run a program trying to detect them and so on. But the numbers are just not there yet, right? So, and there are issues with like maybe the duty cycle of the experiments, maybe the localization capabilities, because also that's the other thing. If you have a BNS event, but the sky area is 1,000 square degrees, it's more difficult, right? So the way my approach to it is like this. I think that if or when there is a next BNS event, we should try by all means in all ways to discover the EM counterpart. I think that those programs will continue and we'll try to make a discovery of the second and the third. But at the same time, we should not wait for that to happen to do cosmology. If our goal is cosmology, we should move on, and because we know what we will do when that happens, right? We exactly that part of the program, I think is very clear. But I think that what I have seen in terms of the development in the last few years is that we have shown that we don't have to have that to make progress in cosmology.
Thank you.
Thank you. And there is a question in the chat. To measure H naught from gravitational waves, black holes, events, you would need the redshift to those sources. How do you measure or calculate redshift?
Okay, so for that, I think you're talking about the BBH events. Okay, so that in that case, you don't have EM counterparts, but what you have is along the line of sight in the region where you think that the event came from, you have a distribution of galaxies, and each of those galaxies have a redshift, and each of those galaxies have a probability of being the host. And with that, you can build a not too complicated likelihood analysis that will take those redshifts and those probabilities into account, and you get to a posterior distribution. You can imagine a simple way to imagine this is that instead of having one galaxy with one redshift associated with one object with one distance, you now have, a pool of galaxies, each of them voting on a different redshift with different weights depending on the probability of that galaxy being the host.
Okay, thank you. Another question. In evaluating prospects, do you account for the finite duty cycle of the LIGO-Virgo detectors?
Yes, you have to if you want to make a quantitative estimate of how many events do we expect and what is the cosmology constraint that we expect. I didn't show any of those forecasts except for quoting what was done in that very first slide in the introduction. If you want to do that properly, yes, you have to take into account some estimate for what's the duty cycle of the detectors, not only their sensitivity, but also their duty cycle.
Okay, thank you. Any other questions?
I have one. I also joined late, so I may have misunderstood, but I heard when you were showing the contours that you said that in one of the plots the tension is not there. I assume you were talking about the Hubble tension. Could you say a bit more about that, please?
Yeah, sure. So what I meant was that this late versus early universe tension, oftentimes it's referred to as actually two tensions, one on the Hubble constant and the other one on the clustering. It could be sigma 8 or S8, right? And what I was saying is that on the clustering, the tension is today less. Actually, it's basically gone compared to what it was maybe in the papers from 2021, 22. That's what I mean. And that is because our analyses have improved. our understanding of systematic uncertainties for the weak lensing analysis have improved. And so the results that were produced since then, and not only from DES, also from kids and other surveys, they are in better agreement with the CMB for that one parameter, the clustering. For the H naught parameter, on that side, the tension is still strong, if not stronger today than it was in 2022. That's what I mean.
Okay, cool. Do you have you're on a paper that explains these results? Can I go look for that online? Probably I'll find it.
Yeah, I think that if you
Or you could just
Okay.
share it on the chat if
yeah,
there
yeah.
is something,
So
or maybe I could
there
reach
is a
out to you.
paper where I think actually there are quite a few people in this call who were in that paper. It's a review paper. I think it's called Cosmology Intertwined.
Oh, I did read that. Okay,
Yeah,
I'll go
exactly.
back
So
to
that
that.
explains
Okay,
well
cool.
all of these sources of tension and so on, right? And then if you look at the latest DES paper, the one that was one of the results, the slides that I showed, the DES cosmology results paper, there is a very thorough discussion of the tension on, or the lack of tension in sigma 8 and so on there. So that's also another place to look for, specifically for that sigma 8 agreement and so on.
Okay, cool. Thanks a lot.
No
Thanks.
problem.
Thank you. Let's the last question is in the chat. Can dark sirens be used to measure the sound horizon size?
I don't know. Yeah, I actually don't know. Maybe there is a way or a method out there that I am on the top of my head, I'm not able to come up with. Maybe somebody else in the call have an answer.
I mean, probably not by themselves, but if you
Yeah,
want.
exactly. I think as part of a combined analysis with other things, you are always going, or we hope that you are going to be able to improve constraints, but I don't think on their own.
Okay, so thank you so much. I think we can thank Marcelle again today.
Thank you. Thank you. It's been a pleasure.
Thank you. Bye, everyone. Bye-bye.